loosen up now after all these formal introductions. I hope my speech is quite informal. I hope it's entertaining, and I hope you can get what you came here for after my speech and after the event. The title is the same. It just happened that I had to send an email this morning to the UK to send me the proper presentation. I'll talk a little bit about the Knowledge Center for Materials Chemistry, which is a conglomerate between a few entities, including my university, Manchester University, Liverpool University, and Dasbury Laboratory, which is the national laboratory one of the national laboratories in the UK. Things don't happen, and inventions don't happen with one-man band. There's a host of others that I would care to mention, and they come from all the different entities involved in this Knowledge Center for Materials Chemistry. Although it's a virtual center, it's a hands-on center. We deliver about 150 odd projects ranging from 6 months to 3 years. In terms of funding, they range from a few thousand to 15 million pounds. The whole talk today is about three types of the so-called smart materials. One class is piezoelectric, the other class is photovoltaic, and the other one is the one that we have embarked recently, and I feel very happy to disclose our findings. These are called triboelectric. Yeah? So I will touch upon all of them, and then I'll tell you how we have integrated all of them into single structures. Starting with the piezoelectric effect, some of you may know it as the ultrasound effect, which is, you send voltage into a piezoelectric transducer, and the piezoelectric transducer starts vibrating. Vibrations called sound, and acoustic waves go through a material. It's usually used in non-destructive testing and also in the medical field. The reverse phenomenon is what we are going to be talking about, is harnessing all these vibrations and seeing how we can get out of the material system electric current. So the piezoelectric effect is nothing new, as you can see, going back to 1817 by Charles Coulomb. It was discovered, and then if you follow the timeline, the last of the ceramic-based ones are the lead zirconate titanate, and the new ones, the piezoelectric polymers, are based on PVDF. This was discovered in Japan in 1969. Again, we knew all along that the piezoelectric materials some of them are natural materials: bone, tendon, silk, wood, and the last one, quartz, which of course you know about the quartz watches and the mechanism that is included. The synthetic piezoelectric materials, you can classify them in two strands. One is ceramics, the other one is polymers. The ceramics, the PZT stands out, and I believe there is a talk later on PZT. The problem with the ceramic-based ones are they're not very flexible, as you know. and some of them, they contain lead. On the right-hand column, you can see the polymers, and one of the best ones is the polyvinyl fluoride, or the so-called PVDF. The difference between them are, as I mentioned, existing ceramics there are fibers, ceramic-based fibers, but if you bend them more than 30 degrees, they snap. So they're good as fibers, but they're not good as for making flexure type of materials or textiles out of them. So they are rigid and brittle. They cannot be knitted, woven. They need to be embedded inside a further polymer matrix to be more flexible. Polymer-based fibers, they are extremely flexible. The mechanical strength is quite high. Let me remind you, PVDF has been used in the construction industry. It's quite hard material, and it's it can withstand UV exposure, etc. They can be knitted, woven into complex two-dimensional and three-dimensional structures, and they can provide high comfort, wearable comfort. Sorry, that's the type of piezoelectric fibers that we've come up with, that you can bend them into usable structures for textiles. If we go back into the theory now of piezoelectric ceramics versus piezoelectric polymers, if you look at the column of the PVDF film, what you can see is that the T31 constant is about 23 for PVDF, where for PZT is 110, which is 5 times higher. As it is, I will take you step by step, and I'll introduce you what we have done to make PVDF as good as PZT. And the barium titanate, where the T31 constant is 78. If you look at devices and piezoelectric generators, going back into 2006, the output was 9 millivolts, and over the years, as you can see, it exponentially moved to 57 volts. Again,
do islet cells make PDL1?
They show more profound outcomes from our piezoelectric nanogenerators. They, back in the 2012, in order to get the 57 volts, as you can see, the structure is quite cumbersome.
Yeah.
It contains ITO. ITO is scarce and quite expensive. And in our case, we try to make something that is made out of a polymer material, something that it can be processed very quickly, cheaply, and it can be used immediately. Looking at the chemistry of PVDF, for those who are interested, in PVDF there are 4 phases that they exist: alpha, beta, gamma, and delta. If you consider the beta and the gamma phases being the piezoelectric, the beta is the better one. So the alpha phase, they are non-polar centrosymmetric. Beta phase, cells packed in parallel planes after stretching and extrusion, and I'll give exactly the criteria for making PVDF beta phase up to 95%. So the whole essence is to turn the alpha phase, which is in the form of granules on the left-hand side there, into beta phase via processing it. So the granules, at the end of the day, they become a fiber structure that can be used further. There are 3, well, you can make PVDF, as some of you may know, if you stretch it and then you cool it. Yeah? So you don't need the high voltage there. However, this is not a permanent PVDF piezoelectric structure, because although the molecules have been aligned, any variation in, even small variations in temperature, they will knock the molecules back into the original into the original state. So in order to lock the beta phase, you've got to apply a high stretching ratio at an elevated temperature and apply high voltage as well. And by the way, this is our first patent, online polling of piezoelectric PVDF filaments. So what is this magic temperature on the PVDF side that you can use? It's just below the Curie temperature. As you can see from the left graph there, it's about 175 degrees. And if you look at the drawing ratio, means how much you can stretch this material, going from granules into the fiber. This ratio, the drawing ratio, is 5 to 1, as you can see on the pic up there. So this is what applies to PVDF as without any additions in it. The higher the beta phase in monofilaments, the more piezoelectric the material is. So what we have achieved in our laboratory is taking the PVDF and raising into 85 to 90% of beta phase. This is by using the stretching ratios and the temperatures that I've mentioned. If you look at the D3 coefficient, if you follow the exact procedures, you end up with a coefficient of 60, which is nearly 2.5 times than the one quoted in the literature for PVDF films, not fibers. When you try, though, to get the voltage out from the fiber, you end up with problems. You have to attach electrodes, and these electrodes are they've got poor fatigue resistance if they're metal foils, and they do break under repeated mechanical deformation. So we had to move away from electrodes being attached on every fiber. Therefore, we had to create a different structure, textile structure, which will give us the textile PVDF textile that we wanted. And in a minute, I'm going to show you where we attach the electrodes, etc. So on the left side, we started with two cones. One has got PVDF, the one at the bottom. The one at the top has got silver. This is a silver thread. So basically what you do is you take them through this knitting machine. It's a standard knitting machine. And you knit this 3D structure that you can see on the right-hand side. This 3D structure has been also patented. Yeah, the process of making it has been patented. So what the structure has is top and bottom electrodes made out of silver threads, and the middle structure is piezoelectric. It is in such a way, it is knitted in such a way so that if you press it, it will give you voltage and current outcome. You look at the production rates of this this textile structure. First the fiber. up to 500 meters per minute. This is using the existing extrusion process, but of course you can scale it up 10 times from 10 to 15 meters per minute. 3D spacer fabric, the production rate is up to 70 square meters per hour. What we found is that the final structure has got excellent compression and resilience properties. The fiber structure is lightweight and completely flexible. Looks and feels no different to ordinary fabrics. And again, on the right-hand side, you can see the silver threads, top and bottom, and the PVDF fibers in between. So what have we achieved by doing this 3D structure is 5 times higher power output than the two-dimensional one. Yeah? On the right-hand side there, what you can see is a high stable output. This is very important because what is happening, as you know, with the piezoelectric, any piezoelectric, say, cantilever scenario, when you press it, it doesn't give any voltage. When you release it and it flaps back, that's when you get the voltage outcome. Yeah? So if you do this once, you're getting a spike. Yeah? The energy you want to collect is what is under the curve. But because this is a very narrow band spike, the energy is not that big. Therefore, somehow you've got to make it into 3D structure so that you can get a stable output. And you can see in this slide in the middle that the green line represents the two-dimensional piezoelectric textile structure, which of course, yes, it is flexible, it can flap, but when you press it, it doesn't give you any outcome. Yeah? Where with a 3D piezoelectric textile, you end up with 5 times nearly the outcome. As I mentioned before, it's quite flexible structure. The compressibility is ranging from 0.02 megapascals to 0.013, and some indications of flexural rigidity also. How do we enhance the piezoelectric properties? And much like in any other material, what you do is you add certain nanoparticles. Zinc stannate is the nanoparticle that we chose to add. And by small additions of zinc stannate, we ended up with higher beta phase content. If you look at what we have achieved using different concentrations of zinc stannate nanoparticles is up to 9 volts outcome and D33 of 127. If you go back into the slide that I've shown you, we started with 23, and by stretching it and making it into a fiber, we got into the 60s, and now we double that with zinc stannate nanoparticles. I'm going to move a little bit away from the piezoelectric into the triboelectric. This is our very new development in our laboratory. So if you take an acrylic film, which is the blue film, and if you add a structure of zinc stannate on the other side, zinc stannate within a PVDF structure, then what you do is you end up with a scenario where, a compressible scenario, whereupon when you compress it and one starts touching each other, it gives you a higher voltage output. I'll show you the some of the results. And these are meant to be in different spaces. In other words, we change the height between the friction parts, and as you can see, the voltage output, peak voltage output, has increased to nearly 400. The voltage outputs that we used to get were from 9 volts to whatever, but now, as you can see, with the triboelectric scenario, you end up with a much higher voltage output. Spacing, of course, plays a very important part, and of course the amount of vibrations you exert on the system. Some of the findings, again, in the laboratory, they go up to 1,200 volts. They are repeatable, but we are trying to make this whole structure into a 3D textile structure. I'll move on quickly. Again, these are findings that they confirm that the triboelectric is much better as a nanogenerator than the PVDF material. So far, what we have achieved in our labs is continuous piezoelectric PVDF monofilaments, multifilaments, and also tapes with high beta phase of up to 90% and high spinning rates up to 500 meters per minute. We developed the 3D spacer technology based on, this is a world's first truly piezoelectric fabric. It says patent applied for, we've already got it. Excellent compression and resilient properties. It's all fiber technology, lightweight, etc., and it feels much like any other fabric, and it can be produced for up to 70 square meters per hour. Now, some of the applications of this fiber technology, one is piezoelectric material for one of the biomedical applications, which is a glove. The idea is to stabilize someone's tremor so that they can touch a cup and drink coffee, or so that they can press the right key on the computer. This technology was based on other inventions that they are used in the sports industry. Tennis rackets. The company is called Head. They were the very first ones to develop the system. What they do is they use 2 piezoelectric films. The first film takes the hit. When you hit the ball, all this energy is transmitted into the other film. That film starts vibrating and counteracts the vibrations of the first. So there is no vibrations coming into your elbow, so you theoretically and practically you don't get tennis elbow. The same technology was put also on the golf clubs. Again, they are using 2 piezoelectric films to achieve that. In our case, we only use single fiber to both take the hit, take the vibrations, and then put them out of phase. So this is another pattern that we have. Another application is on carpets. This is the bringing out the third direction. So when you have a 2D structure or a 3D structure, it's basically on this direction. The Z direction, which is the carpet, is fibers sticking out. There's a lot of energy that can be extracted from a 3D structure as a carpet. By the way, these are carpets that they are in the Terminal 5 of Heathrow Airport. They are not piezoelectric. They are from our own material that came out of our laboratories, which is heat resistant material and that is capable of reducing flammability. This is one of the potential applications. Lots of other people around the world, researchers, have moved into making a structure where you can put into your shoe and you can give off energy. They are using different techniques. The latest one that I saw came from the MIT labs, and ours, which is the 3D textile structure. If you look at the bottom left side here, it can be used as a false sensor. So if you put an undercarpet layer, you can find out if a person, being your mother or grandmother, is happy walking on it, happy waking up in the morning, and if they fall down again, you can pick up you can pick that up. Tires is another application that we have been aiming at. We are talking to Intercontinental. The idea is to put these fibers within the structure of the tire and try to obtain as much energy out of the system as possible. And we are talking about a different kind of tire that hasn't got any air in. Maybe some of you may have seen this, not in the market, but as a prototype. Again, in biomedical applications, you can put this textile patch in good use in picking up heart rates, etc. But also you can use the technology. Theoretically, we haven't proven that yet. That if you put it in the bloodstream and if the flow is, you can make it turbulent in certain areas, so that you can extract vibrations from the flow. Why I started talking about piezoelectric first is I'm assuming that most of you know about the photovoltaic, and the question that we asked ourselves early in the piece was, can we make a material which is hybrid, has got both piezoelectric and photovoltaic properties? Where we come from, being in the north part of the UK, we don't see much sun. So that's why we endeavored in creating energy out of wind vibrations and rain also. So I'll talk a little bit about the photovoltaic. Again, the innovation here is that we put the photovoltaic, organic photovoltaic structure on a fiber. We used both heterojunctions, bilayer and bulk, and we used the system by which we electrospan material, evaporated, put the activated layer, dry it, anneal it, and going through this repeated process, we ended up with both films and fibers. as you can see, the structure is quite complicated, but again, at the end of the day, quite flexible. We did all the necessary experiments for, illumination experiments, etc., to find the Pmax, and this hybrid structure, the piezoelectric and photovoltaic structure, we finally got it into a stage where we feel that it can be a commercial, potentially a commercial product, and we were struggling with applications. Tata Steel is very keen on incorporating this structure on rooftops. Lampposts also, garden lights, traffic lights, bus stop shelters and train stations can be utilizing this material. One of the biggest applications, I think, is the artificial tree. If you make fibers and you chop them into lengths of, let's say, 5 or 7 centimeters, this is the optimum length that we found, that when you put it into cantilever type of scenario, you get a lot of outcome after pressing it or after heating it. So if you have lots of fibers in a stem and under rain conditions, and we have done this experiment, you start producing quite a meaningful voltage and current. The same happens during wind. So you get wind usually and rain, especially in the UK. Now, applying the photovoltaic structure on top of it, you get the benefit of the sun. Now, you can appreciate that a tree of roughly about these dimensions will have a lot of surface exposure to the sun, much bigger than 10 panels put together. But you can get a double effect by putting mirrors on the ground, so that you can get reflections from the sun from the ground and nearly double the effect. Another immediate application is on sails. Usually sail ships, they've got 40 square meters of sail, so that's 40 plus 40, 80 square meters of exposure of sun. Remember, when the sail is fully blown, you don't get any piezoelectric effect out of it. So some of the conclusions, and for the very first time, continuous flexible piezoelectric filaments that have been successfully produced. 3D spacer technology, again, we have improved it by adding certain nanoparticles in. For the first time, flexible hybrid piezoelectric photovoltaic films and fibers have been successfully produced and tested. It says 5 international awards, but we have received more than 10, 11 international awards on this technology. In 2013, Fibre company was established to provide us with research funding, including private and government funds, to move it out of the laboratory into the commercial world. There's a lot of publications, but most of the notable ones are listed here. So that's what I had to say so far, and I guess we have a few minutes for questions. So I'll be happy to. Yes.
Thank you for the presentation. Very interesting topic. You mentioned that the 3D piezoelectric that you advocated produces constant voltage as well.
No.
Not constant?
No, it doesn't produce constant, but we can take it. Each fiber, yeah, does not produce constant, yeah, but the whole structure, because we put silver on top and silver on the bottom as electrodes, then we collect all this, yeah, and it doesn't give you constant constant voltage. Yes, yeah.
So what is it just higher than the regular piezoelectric, right?
Sorry?
Thanks a lot. It is just higher than the
Yes.
the conventional piezoelectric, right?
Yes.
Okay, because of 3D structure. And one more question: these material are available in the market because you said that there is a company.
I've got no. Sorry, it's not in the market. But if someone wants to buy and test it, yes, we can provide that. We haven't.
Okay.
Sorry, Fibre hasn't set up production lines yet.
Okay. Yeah. Thanks a lot. Thank you very much.
Morning. I'm sorry I'm a bit late because I just arrived to Philadelphia, unfortunately.
Yeah.
What about the mechanical properties, please?
Sorry.
The mechanical properties.
Yeah.
I mean, is it necessary to have such a limit of mechanical properties? Thank you.
Yeah, I'll talk first about the photovoltaic structure on top. It is quite sensitive, so in order to protect it, you've got to apply another surface see-through type of material. Yeah. However, if you scratch it, it's not usable anymore. Yeah. So I thought I'd clarify that as for the photovoltaics. For the PVDF material, it is quite hard. It is used in the construction industry. It is used in moving bricks from the lower ground to top of the building.
Yeah,
So
I guess that's good.
Yeah.
Thank you very much.
Yeah. Thank you.